Hello everyone, I am Brony Kalk, and today I'm going to be doing the second of the quote-unquote easy problems from this year's United States Math Olympiad, number 4, and it goes a little like this. We're given some circle, they specify that it's the unit circle, but it doesn't really matter all that much, and we know that there are 2n distinct points on it, other than the point, well they call it 1, 0 here, but it's just some point on our circle. And yes, this is a circle, don't question it. All circles actually look like this. Big government's been lying to you. So, then we have to color these points. It says 2n, but I'm only going to draw 2 times 4 or 8 because that's nice and simple. And we have exactly n of them are colored red, so that's going to be 4 reds. And exactly n of them are colored blue. So that's going to be, let's say, here, 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 and here. And then we want some ordering of the red points. It doesn't really matter. So we have R1, let's say, R2, R3, and R4. So, then we want to start with R1 and start going counterclockwise until we find a blue point. And first one we find is this one, so we're going to call that blue 1. Then we start with R2, we go around, blue 2. Then we go to R3 and we start going, and we notice this is already labeled, so we keep going, and we find blue 3, R4, can't use that, so this must be blue 4. And the problem wants us to show that no matter how we chose to order the 4 red points in the beginning, we will always have the same amount of arcs going from Ri, so like R1 to B1, and so on and so forth. We'll always have the same number crossing the point 1, 0, that point we weren't allowed to use before. So, in this case, we have 2 crossings. So, pretty simple. Well, so far. But perhaps it would help to rephrase this problem, because if I just say, because the way it looks at this point, it sounds like it wants us to take all possible orderings and just count them in some way. And there's probably some way of constructively counting it that's nice, but there's a much easier way to do this. Let's just start with some order, like this one, for example. And we know how many crossings it has. And we want to show that if we change the ordering to some other ordering, the number of crossings isn't going to change. It's the exact same problem, just worded in a way that makes us think of the solution a little quicker. We want to find a way to change this ordering to any other ordering. And then we want to show that when we change the ordering in that way, the number of crossings does not change. So this was just an example to get us oriented, know what we're looking at, more or less. So I'm going to erase it now. And we need to think of a way to start rearranging our sequence. Well, let's start playing around with some small sequence, like just 3 numbers, 1, 2, and 3. What happens if we switch 2 of them? So let's switch the last 2 and we get 1, 3, 2. If we switch the first 2, 3, 1, 2, 3, 2, 1, 2, 3, 1, 2, 1, 3. As it turns out, that's all 6 possible combinations generated just by switching 2 that were right next to each other. And so now we're thinking, maybe this works for all of them, and it's actually quite easy to show it does with induction. I'll leave that as an exercise for the viewer. But back to the problem. We now have our technique. We want to show that if we switch any 2 consecutive terms in our ordering, the number of crossings doesn't change. So, how are we going to go about that? Well, let's just take not the whole circle, but just an arc of it. And we have RK and RK plus 1, which are the ones we're going to switch at some point. And we have blue K and blue K plus 1. So, what does that look like? Well, there are two possible scenarios. We have RK here. We have RK plus 1 here. Where do the blues go? Well, this is just some generic arc, so we can say with certainty that it's going to either occur counterclockwise. Blue K will occur before RK plus 1, or let's draw another example arc. It'll occur counterclockwise after RK plus 1. So we have these two cases. And then we know that blue K plus 1 has to occur counterclockwise after RK plus 1. So, now we can proceed with our problem. We're going to take each of these cases and we're going to show what happens when we rearrange it. So first, let's consider everything before RK. So, everything from R1 to RK minus 1 and all the blues associated with that. They're already labeled. If we're going to switch these two, we're not messing with anything before it. So we don't have to worry about any blues or reds that may fall before or after that. And the ones after that, well, as it turns out, well, let's consider what happens if, say, we have blue K plus 2. Where can that go? We don't even know where RK plus 2 is. We don't even care. Where does it fall? Obviously, if it falls before BK, then we've done something wrong, because this is unlabeled and we're moving from here. So this shouldn't be BK if that's the case. This should be BK. So it's after BK and it's after BK plus 1. So it actually doesn't matter or where or any of the blues after BK and BK plus 1 are. They're well outside of what we need to consider. So now let's start messing around with these. Let's switch them. So let's start with this case. We have these arcs to begin with. We notice that they intersect here, so we have one arc here, two arcs here, and one arc here. And then we have a bunch of our arcs that don't change. And we want to switch these. So I'm going to call this R prime K and R prime K plus 1. So we start with R prime K, and the first thing that shows up here is blue K. So we have B prime K. And then we go here, R prime K plus 1, it's going to be looking, we find B prime K plus 1. So now we have a new set of arcs like this. And let's consider what's happening here. We have one arc, the arc for each of these going from the red to the red. Then red to blue, in both cases, we have two arcs. It's just which of the two, it's just this has changed. So we have these two arcs here, we have these two arcs here. And then afterwards we have one arc again going from blue to blue. So in other words, no matter where the 1, 0 point falls in this, if it falls outside of it, obviously nothing changes. If it falls here, still one arc, still two arcs, still one arc. So for this case, it doesn't matter where 1, 0 is on this scale. It's not going to change anything. Then we have here. So let's say you're RK plus 1 prime and you are RK prime. Forgot to draw the arcs at the beginning, but So k, I know it was this arc and this arc. So we start with r prime k, we start looking counterclockwise, and we find b prime k, which was just bk plus 1. And we go back to rk plus 1 prime, we start going through, and we find this point here. So our arcs are actually exactly the same as they were before, just in a different order. So nothing changes here, and 1, 0, or the number of crossings is unaffected. And we see that that works for both cases. So we know that we switch any 2 points that are right next to each other in the ordering, we're not changing the number of crossings. And if we do that over and over, we can get any sequence we want. So we're done. It was a nice, simple problem. Actually, yeah, I would consider it easier than problem number 1. And just because of the lack of technical knowledge that is needed for it. But it was still a really fun problem, and I enjoyed doing it during the test, and I enjoyed doing it here. If you enjoyed seeing me do it, consider leaving a like. If you think I'm good, I'm complete garbage, or just have any ideas for me to improve, or any problems you want to see, you just send me a comment down below. I'll try to get back to you as soon as I see it. And if you like what I do, you checked out some of my other videos maybe, and you're interested in my stuff, consider subscribing and hitting that notification bell. Anyways, thank you for joining me, and I will see you next time.